Now I'm going to explain single phase full wave control rectifier for both center tapped and bridge configuration with RL load, right? So in this analysis, I'm going to consider the continuous conduction mode. Let me suppose it as continuous. Let me write it as continuous conduction mode. Fine, continuous conduction mode without freewheeling diode. I am not going to place any kind of freewheeling diode, right. So whatever the analysis which we have been made in the RL load, for the RL load for single phase half wave control rectifier, the same analysis we are going to consider. At particular alpha and pi plus alpha, I have given the triggering pulses. Understood? Or I have given the triggering pulses, right? So now what I'm going to consider, so this is going to be happen like this. So when alpha, see, same analysis, positive half cycle and negative half cycles, try to watch the previous two videos so that you can easily understand what I'm saying, right? So when T1 is triggered for center tap transform, I'm saying Yuma, and for if for bridge configuration, both T1 and T2 are triggering, right? So what is going to be happen? So there is a voltage which is going to have like this. The input voltage is going to be getting like that. Means what? In the positive half cycle, V naught equal to positive Vs. In the negative half cycle, V naught equal to negative Vs. Right? Understood over what I'm saying now? But due to the presence of inductor, the current will not be tending towards zero. It will go up to some time, right? It will not go, it will go up to some time. That is nothing but what? Pi plus alpha. See, continuous conduction mode, there are two ways of representing this, right? How it is. So when T1 is on position, it is moving like this, and when the T2 is off, I mean T1 is going to be get off, so inductor used to discharge like this and like this. So this is what the continuous conduction mode process goes on, right? This is what the continuous conduction mode process goes on. But in some textbooks you can refer the continuous current mode as, right, you can refer the continuous current mode as that, like this, complete constant, right? Continuously it was flowing, right? You can draw any kind of waveform, right? Continuously it is flowing over here. So if the inductor value is highly is more, if the inductor value is very high, then the current is continuous, and if the inductor current is somewhat low, then the inductor current used to flow in this particular fashion. Understood or what I'm saying? So that is the only reason what is going to happen from alpha, right, from alpha to pi plus alpha, right, from alpha to pi plus alpha, we are going to get this particular current, right? We are going to get this particular voltage. Understood or what I'm saying? Again, from see here, if it is a center type of transformer, let me draw it first and then let me discuss it. So in the second half cycle, again you are going to get a condition like this. As the current is completely continuous, right, as the current is completely continuous, you are going to get the waveform like this. Understood or what I'm saying, right? So at this condition, at this position, what is going to be happen? The current in the inductor, the energy stored in the inductor is going to be nullified, is going to be zero, right? So here negative polarities will appear across this particular T1, so thereby T1 T2 is going to be turned on, right? Same analysis we are going to do for see, if it is center type of transformer, then here T1 is conducting, here T2 is conducting, right? If it is bridge type configuration, right, if it is bridge type configuration, here T1 T2 will be conducting, here T3 T4 will be conducting. So this is what the what I mean to say, the continuous conduction process. Current is not getting zero at anything, right? Current is not getting zero at anything, at anywhere. So that is nothing, that is the only reason it is nothing but what? Continuous continuous conduction mode. See, without freewheeling diode, see, from pi to pi plus alpha, this spike is there, right? So definitely this spike is there up to the firing angle, new firing angle alpha. Very simple analysis if you go through in a proper fashion, right? If you go through in a proper fashion. And see how we are going to draw the wave, I mean Thyristor voltage waveforms, right? Thyristor voltage waveforms. See, this is the how we are going to draw the Thyristor voltage waveforms. Let me draw it for a while. See, this is omega t, right? This is omega t, and this is alpha. Sorry, this is alpha. Yeah. So I'm going to draw for VT1 for center tap configuration, VT1 and VT2 for bridge type configuration. Please kindly note my things here, right? So from alpha to pi plus alpha, Thyristor C1 and T2 are conducting. That is T1 is conducting. That means from alpha to pi plus alpha, it is going to be 0 from alpha to pi plus alpha, right? So from pi plus alpha to how much it is? I think it is up to 2 pi plus alpha. From, see, don't confuse with the terminologies, right? From 2 pi plus alpha, from pi plus alpha to 2 pi plus alpha, T3 and T4 are conducting. That means T2 is conducting, but there is some voltage across the Thyristor T1 or for center type configuration, or Thyristor T1 T2 for bridge type configuration. So from pi plus alpha, right, this is from alpha, this is from pi plus alpha up to, from pi plus alpha to 2 pi, from pi plus alpha to 2 pi, so this is I think 2 pi, and up to 2 pi plus alpha you are going to get like this. So finally, and then it is 0, and then it is 0. So before alpha, VT1 is having some kind of voltage like this. So simple case ma, this is 2 pi and this is 2 pi plus alpha, this is 3 pi, this is pi, this is nothing but what I'm writing clearly, pi plus alpha, pi plus alpha. Understood or what I'm saying? Now if I draw the waveforms of, right, if I draw the waveform of VT2, right, again this is alpha, this is pi plus alpha. Please draw it clearly, 2 pi plus alpha, 3 pi, fine. So again from alpha, see, when T3 and T4 are conducting, from pi plus alpha to 2 pi plus alpha it is conducting. So from pi plus alpha to 2 pi plus alpha, T3 is 0. I mean T3 T4 are 0. Similar for bridge type configuration, and for center type configuration T2 is 0. Understood over. And but before it has some value, so before it is having some value, that is from after like this up to pi you are having, and then we are having like this. Understood over what I'm saying? And up to after 2 pi plus alpha, again you are having some kind of voltage up to 3 pi. Sorry, I have not drawn clearly here. Wait for a while. Fine, understood over. And then up to 2 pi, and then we are going to get the values like this. So hope you understand what I am saying, right? Hope you understand what I am saying, right? So now let me derive the output voltage equations, average output voltage equations, and for this particular continuous conduction mode without freewheeling diode, right? Without freewheeling diode. Now let me derive the average load voltage of what? RL load, that means single phase full wave control rectifier RL load for both the configurations, right? So how we are going to get? So V naught average equal to, we know the formula for it, 1 by T integral 0 to T V naught of T into d omega T. So that implies, what is the time period here? 1 by pi, we have been studied in the previous video itself. 1 by pi integral alpha to pi plus alpha. See, this is the conduction period, alpha to pi plus alpha. I have not mentioned clearly here, alpha I think, right? Alpha to pi plus alpha, Vm sine omega t d omega t. Understood over what I'm saying? So that equal to what is happening? So Vm by pi, right? Vm by pi integral, I mean minus cos omega t sin omega t integral is minus cos omega t under limits alpha to pi. Same analysis ma. So again Vm by pi into minus cos phi. I think it is pi plus alpha. Yeah. Minus of cos pi plus alpha minus cos alpha, right? So minus cos of pi plus alpha is nothing but minus cos alpha in the sense what, 2 cos alpha, that is Vm by pi integral minus of minus cos alpha minus cos alpha. Fine. So minus into minus of minus will be plus. So minus 2 cos alpha minus into minus will be plus. So finally V naught average equal to what? 2 Vm by pi into, right, cos alpha. Right, 2 Vm by pi into cos alpha. In this way, we are going to calculate the average output voltage, average load voltage for a single phase full wave control rectifier with R load, either it is center tapered configuration or bridge type configuration, right? So try to find out the value of RMS load voltage, so it will be a good practice for you people, right? Thank you.